Well, this is meant to be a review session, so I don't really have slides. I don't know if you can see this from far away. But I think first thing off, I'll repeat what Rachada said. If you have had trouble with Lab 3, definitely go and see the TAs for Lab 4. Get started on Lab 4 early, but after the exam, hopefully. The exam is Wednesday. It's going to be in this room at 12:30, and we're going to likely take the entire 2 hours. So I'll keep you until 2:30. Is that good with everyone? Okay. And the information I sent out during the weekend, I think, or on Friday, I'll go over that briefly. But I think the 12 exam here, as you pointed out, is the same as the 13 exam. Oh.
Just go back to the previous year.
Yeah, say it again? Oh, it's just broken. Okay. Yeah, we just have some broken links here, Rachada. Can you fix these? So this one is spring 2012, but this one is not correct. Just don't put out the solution for the exam on Wednesday. Say it again? These solutions should be there, I think, though. Oh, that's spring 2012. But I wouldn't recommend, yeah, spring 2013 doesn't work. Okay?
I'll fix that.
Okay.
While I'm fixing that, you can go into spring 13.
Yeah, I know. So I'll open this window. But you can find all the exams from spring 2013 and spring 2012 from last year's website. If you go to exams and last year's website, you can see the spring 2012 exam, its solutions, and spring 2013 exam and its solutions too. But let me give you some information for the exam, and then I'll take any questions you ask. If you don't ask any questions, we'll end early so that you study for the exam. Okay? So basically, let's see. Oh, I guess I cannot. Yeah, I already said the first one. Please try to come early. If you come in at 12:25 p.m., then we won't disrupt anyone's exam. Okay? This is going to be a relatively tight room because we have around 40 students, and we need to fit everyone here. We'll probably add another row over here. But if you come in late, you'd be disrupting not only your exam, but others' exam too. Okay. It'll be closed book and closed notes. Hopefully you know everything well that you don't need any notes anyway. You'll be able to make the trade-offs. Figure out, for example, what kind of changes are made to the data path in a design. You don't need notes for that, right? Yes?
Do we come to class early on March 6th?
Oh yeah, that's wrong. That should be March 5th. Could you fix that as well? Yeah, that's not early anymore, absolutely. Actually, there's no class on March 6th, so. That's right. You can fix that too, right, Rachada?
Yeah,
Okay. I don't know if you'll be able to enforce this one. Please sit at least one seat between you and any other classmate in any direction. That's right. Try to do that, but I don't think it's going to happen in this room. But you've all signed the honor code anyway, right? Even if you haven't signed it, you know about the honor code. It's all your own work, right? Okay, you can bring a single 8.5 by 11 sheet. You can write anything. There was a question whether you can type it. You can type it in any font you like. You can even bring a magnifying glass if you wish. But it's up to you. But just one sheet. And all topics we've covered by March 1st, which is last Friday. Including last Friday will be on the exam. Can be on the exam. Of course, we're not going to be able to ask every single question that we can potentially cover, right? Actually, Friday, February 28th. That was February 28th, right? That's right. Yeah, this includes lectures, labs, homeworks, and required readings. Now, this doesn't mean that I'm going to ask you a specific question on a particular required reading. That's not fair. But the gist of the reading, for example, the microarchitecture of superscalar processors, that helped your understanding of the out-of-order execution concepts, right, or precise exception concepts. So those will definitely be tested. I can guarantee you that there will be a question on out-of-order execution, for example. But you can take a look at the past exams and predict the future based on the past exams too. So I didn't give you any new information if you have a good predictor. Okay? Let's see. Well, I already talked about that. But if you look at the past exams, which I may go over very briefly, But we have the solution, so I would rather have you solve the problem rather than me solving your problem in front of you, because that would be a lot better for you, I think. I'd rather answer questions about the concepts if you have questions on them. There'll be a variety of problem solving, design, and trade-off analysis questions, and we'll focus on testing your understanding. Of course, there are some keywords that you should really know, right? You should know what dynamic scheduling is, right? It's out of order dispatch, out of order execution. So that I don't consider as memorization. You should know the difference between superscalar and VLIW without us defining what superscalar and VLIW is. That's not memorization. But figuring out what are the trade-offs between superscalar and VLIW, that's understanding. That's testing understanding, right? I guess VLIW is a way of doing multiple instruction fetch, which simplifies the hardware, right? Multiple instruction fetch, decode, execute. Whereas superscalar is hardware is complex, but compiler doesn't need to do anything. You fetch multiple instructions, decode multiple instructions, execute multiple instructions without having any compiler support. Right? That's one trade-off between them. OK. Well, you can certainly find sample exams over there. If Rachada has fixed them, no. OK, good. Now we'll be able to find them there. So if you do this, we can take a look at them. No. Yeah. If you look at past year's exam, there are 7 questions. And the first question is usually a potpourri where we test your understanding. How do I open this in something else?
You have to download it.
You have to download it?
So,
I see. You have to save as something. I guess exam 1. Let's do this.
Actually, if you want to learn for next time, click cancel.
Let's do that. OK.
Do Command P to print it.
Command P. There you go.
And it should, if you scroll down, it should say Open PDF and Preview at the bottom.
Oh, wow. And Preview, though. What about Open PDF and Acrobat?
Why do you use Acrobat? I'm just kidding.
All right. Because Preview sucks? Could that be a good answer? OK, Preview. You wanted Preview, so we'll do Preview. Thanks, though. So how do you actually, maybe you can teach me something else. How do you see the full page view in Preview? This one?
Like the ones on the side. Oh, there's that.
Oh, was it this one? OK. But I don't want to scroll within a page.
Oh, you want it to fit inside?
Yeah, fit it. OK, maybe this is OK. Let's do it. Yeah. In Adobe, I have that flexibility. But OK. It's a trade-off between the Adobe developer effort and the user effort. So the first question is usually a potpourri of multiple different concepts. So first of all, the exam will take a long time. I'd suggest that if you are stuck with a question, move on. OK? It's good to strategize and figure out what question you know, what question you don't know. These questions should not take too long. These questions, if you know the concept, well, actually, all of the questions are like that. But if you know the concept, you should be able to write these down. For example, this one says keeping a did we do this before? No? In class? Like a potpourri question is, this one says keeping processor pipeline full with useful instructions is critical for achieving high performance. What are the 3 fundamental reasons why a processor pipeline cannot always be kept full? Can anybody tell what those are? Yes? Data dependencies? OK. That's right, exactly. That's the answer. That's it. So this should take 5 seconds. Yes?
Isn't there another reason which is variable length instruction times for like memory access?
So in that case, as long as you can keep you have independent instructions, it's OK, right? You can still keep the pipeline full. Whereas data dependencies and control dependencies introduce bubbles into the pipeline. OK. Now that exacerbates the effect of data and control dependencies, because if there's a data dependent instruction on that long latency, variable length instruction, it's harder to keep the pipeline full. But it's not a fundamental reason. Make sense? Resource contention is like that also. If you have resource contention, you have to introduce a bubble because that resource is needed by 2 stages in the pipeline. Okay. This is actually somewhere in the lecture notes too. This is directly out of the lecture notes. Some of the questions in potpourri could be directly out of the lecture notes. Okay. We want to do yeah, well, I'll go over these questions and then I'll take some of your questions. But if you look at this, this is a potpourri of different concepts. There's a question on exceptions and interrupts, branch target buffer, return address prediction. A lot of fun concepts. Restartable versus precise interrupts, segmentation and paging. That's another short one if you see that. Out of order versus data flow. Thomas Law's algorithm. This is a fun question. I won't solve it for you because it'll spoil it. But this is one of the example questions that you may get. Here's the state of the reservation station in the processor during a particular cycle. X denotes an unknown value. You don't care about that. There you see the state of the add reservation station, a multiply reservation station, and the question asks, what is wrong with this picture? It's a puzzle, but if you really understand what's going on, you should be able to tell what's wrong with it. Have you solved it? Has anyone solved it? Okay, don't tell it. Don't tell anyone. Unless you want to spoil it for everyone. But this is a fun question, I think. You'll have fun with it. Okay, minimizing stalls. These are all the concepts that we've covered. So definitely expect to get similar kind of questions in the exam. Like Thomas Law's algorithm strikes back. Wow. That was Thomas Law's algorithm also. But this is more of a design question also. If you look at this, again, I probably won't solve it for you, but we give you a design. Based on that description, is there an opportunity to improve the performance of your friend's design? And then you ask what type of code leads to inefficient execution in your friend's design and why? And then we ask you, what would you recommend to your friend to eliminate the inefficiency? If you cannot actually improve the design, then explain why not. Okay? So I definitely recommend going through this exam. And then the later questions, of which there are 6, I think, in this exam, are longer questions that require more calculation. Actually, potpourri questions could require calculation too, but they're meant to be shorter questions, quicker questions. This one is on branch prediction and dual path execution, for example. We ask you to write the equation for the number of instructions that are fetched on this machine in terms of the number of correct path instructions in the program and the branch prediction accuracy of A. Again, definitely do that. It's not that difficult, actually, if you think about it. And once you actually do these questions, I think it'll be easier to do the exam questions also, hopefully. Okay. Is this useful? Should I keep going? No? No? Okay.
We're seeing the
We're going to look at it.
Oh, okay. All right. All right. You're seeing the questions. Okay. I'll close it. You don't want these. Okay. Let's see. What else do I have? Okay. Some more tips. Yeah, there will be a review session on March 3rd, which is happening right now. Okay, I already said that. The questions will obviously not be the same. That answers your question, actually. I had the answer here. But their spirit will be similar, or can be similar. Well, I'll tell you that they will be similar. And if you want more questions, more similar questions, you can go into 740 and 742 exam questions too. But then you'll have to dig into what topics we have covered and what topics we have not covered. It's up to you. You have a bigger question base, if you will, if you would like to delve into more. And obviously, we'll ask you about the lecture material and trade-offs. Trade-offs are the soul of this course, as I've discussed in the earliest lecture, right? The ability to make those trade-offs and figure out what's going on in a machine will be what we will ask. There are also buzzwords on the website, if you haven't realized that until now. They're still on the website, right, Rachada? Let's see. So if you go to lecture buzzwords, this would give you a quick idea of what each lecture covered without going through all of the slides. So lecture 1, for example. And these could be things that we could ask you because we've covered in the lecture, right? It may feel like a long time, but it looks like on January 15th, we'll talk about Moore's law, in-order execution. Well, these are high-level concepts, but I think we've talked about retention time, right? DRAM retention time. So hopefully you remember that. Okay. We won't go into detail on that because we have lectures on DRAM later on, but you should know what it is. Okay. So these buzzwords hopefully would be useful. Okay. And I think we have it on for the last lecture too. Is that correct? No, we don't have it for lecture 18, but we can put that up. Okay. I think there was one question, will GPUs be on the exam? They're before March 1st, so yes. That's a topic that will likely be on the exam. And you can interpret that as, yes, it will be on the exam. Okay? It's a hot topic. It's a very hot area today. GPU design as well as GPU programming. So I can expect it to be on the exam. If you look at last year's 447, we've asked it on the first exam and we asked it on the final too. I don't remember if we've asked it on the second exam. Because second exam is more or less dedicated for the topics that were covered after the first exam. Okay, that's this. And yeah, I think we've talked about this. So for the answers, for the potpourri answers, a good rule of thumb, don't take this to extreme, but don't write pages and pages anywhere. Most of the questions in potpourri can be answered. Well, I'm not going to show you the solutions because you don't even want the questions. So the answers should not be long. In most places, we tell you that you should actually answer, be concise. You will be penalized for verbosity. Because sometimes if you write more and what you write is wrong, you'll be penalized for it, right? Just don't throw us lots of things and expect us to pick the right answer and give you full credit just for that right answer and ignore everything else that's surrounding it. That's not the right approach. Be selective in your answer and ensure that you're not verbose, basically. And the questions will be designed such that the answers will be short, usually less than 10 words or 20 words. For example, the first question we looked at, control dependencies, data dependencies. I know I spoiled it for you, but control dependencies and data dependencies and resource contention, it's just, that's it, right? You don't need to say more. You don't need to explain to me what a data dependence is. OK. I think that's all I have. But if you study hard, hopefully you all will get whatever the exam is out of. I guess it was out of 270 plus 45 last time. 315. So there may be a bonus question. I'm not sure yet. And it will be, and you can pick, so this is another way of saying you can pick any of the 7 questions, I guess. And if you do the bonus, then you'll get the extra bonus also. Okay. So all of the questions will have their points. So you may choose to do the bonus question, for example, if you're running out of time, and not do problem 3. Yes?
Will we know the curve like after the exam, or will we know the curve at the end of the semester?
Oh, you'll know the curve after the exam. We'll post the grade distribution for the exam once the exam is graded.
But like what it actually scales to?
Oh, yeah, that will be at the end of the semester. That should give you a good idea of where you stand in terms of the exam. But the semester's grade is really dependent on everything, not just one exam. In fact, this is only 25%, less than 25%, right? 15%, I think. Yeah. But you can talk to me if you would like to know. Yeah, definitely talk to me if you would like to know where this particular value stands. You can have a good idea, but if you really would like to know, just talk to me. Does that make sense? Is that fair? Okay. What else? Otherwise, I can start taking your questions, I think, or any topic that you would like me to go over again. I can go over again. We can do the out-of-order execution example again while it's on the board. But I'm not sure if that's the best way of spending our time. But I'll do whatever you want me to do. Yes?
Can you go for like an example GPU question?
Oh. At the expense of spoiling it?
Oh, like the one that we had on.
Well, maybe not the one on the homework, but just like, I don't know if you can make one up.
Oh, wow. You want me to make the exam up, huh? That's a tough one. So I will recommend you to take a look at the GPU question and maybe come and talk with me, unless you want me to go over that GPU question on the exam. What do you guys want? So we did ask a GPU question over here. I don't want to come up with a new GPU question because that will likely be on the exam.
I guess maybe go over the one in the homework so that then we can do it.
Oh, I see. So that was actually from a past exam. We could do that.
Okay.
Yeah, you have to do it anyway. Let's see. homeworks. So that's what we did. Oh, the one in homework 4, you mean? Yeah. So this was from a past exam. Is that correct, Rashada? Oh, you changed some numbers. Okay. Okay, it's pretty similar to the one in the exam, right? You want me to go over it? Or?
Sure.
Okay. Okay, let's see if I... And we don't have the answers to these yet? Okay. Okay, so this question asks, we asked a similar question on both the midterm and the final last year. So I definitely recommend knowing what's going on here. We defined the SIMD utilization of a program on a GPU as a fraction of SIMD lanes that are kept busy with active threads during the run of a program. Right? The following code segment is run on a GPU. Each thread executes a single iteration of the shown loop. You can see this, right? And if you look at an iteration over here, it consists of this if statement, and there's no else over here. Each thread, okay. Assume that the data values of the arrays A, B, and C are already in vector registers so that there are no loads and stores in this program, just to make your life easier. Notice that there are 4 instructions in each thread. That's the hint. And what are those 4 instructions? I guess 1, 2, 3, 4. That's the assumption. Yes?
We assume that each of these 4 instructions would take the same amount of cycles to evaluate.
I don't think you need that information to answer this question.
Okay.
Yeah, the question will not ask you a number of cycles, unless you've changed the question significantly. OK. Yeah, you don't need that information for this. A warp in the GPU consists of 64 threads, and there are 64 SIMD lanes in the GPU. That's kind of expected, right? 64 threads, they're all executing each one is executing in one lane. The first question here, is how many warps does it take to execute this program? This is an easy one, right? So if you look at the code, basically you have 1 million iterations, right? And each one of is a thread. That's what we told you over here. So you have 1 million threads. And a warp consists of 64 threads. So the answer to this is really easy, I think.
The ceiling of that divided by 64.
That's right, yes. Exactly. And it's divisible, I believe.
It's not.
Oh, it's not? 1 million is not divisible? OK. OK. I think in the exam it was divisible. So so we're trying to change the question such that it became non-divisible. So that's basically the answer, right? Does that make sense to you guys? OK, good. Oh, actually, if you put it that way, that's a perfectly valid answer. If you put it, it's the ceiling of 1 million divided by 64, that's fine. You don't need to calculate anymore. So we'll be flexible. As long as you give us the right answer, we don't need you to calculate that. OK, well, there you go. That's 2 to the 20 divided by 2 to the 6. Yes, it's divisible, right?
The same one on the previous homework?
I don't know, actually. Is it the same one in the previous homework, Racheta? Yeah. Yeah, 2 to the 20 divided by 2 to the 6. I trusted you too much. Yes?
So is that a yes to calculators or a no to calculators?
So no calculators, yes. There will be no calculators allowed in the exam. But that doesn't mean that you have to do this calculation, although it's easy to do this calculation as we just did, right? It's 2 to the 20 divided by 2 to the 6, 2 to the 14, 16,378. Right? OK. OK. When the next question, now it's becoming more interesting. I don't know if I would like to really do all of this question, but is it when we measure the SIMD utilization for this program with one input set, we find that it's 67 divided by 256. What can you say about arrays A, B, and C? Maybe I'll give you hints as to how to answer the question, but I won't spoil it for you. So are you guys OK with that? Yeah. Be precise. Hint, look at the if branch. What can you say about A, B, C? I don't know if we added that hint, or maybe our chata was too good to you. Yes, that's what I figured. So how would you go about solving it? Well, I'd rather give you the problem-solving skill rather than solving the question. Exactly. Yes?
So you know that you will get lower utilization if the branch is not followed for one of them, and obviously it is for the others because it'll still have to go through it, but
yes,
just not execute anything. So you have to figure out kind of what would cause the B of I to be less than 444.
That's right.
In the previous iteration by looking at what's there.
That's right, yes. Does that make sense? Yes?
If, hypothetically, if the branch wasn't taken for all threads, is it still 100% utilization?
That's right. So that's the key. So if you look at this, you either execute 4 instructions or no instructions, right? So for a thread, if the branch is taken, you execute 1 instruction. If it's not taken, you execute 4 instructions, right? Does that make sense? Because the branch is 1 instruction. So if you have a warp where all of the branches, well, I guess let's do not taken or taken. If you have all of the threads not taking the branch, all of the threads will execute the branch. So your SIMD utilization is 100%. Right? Make sense? If all of the threads take the branch, then all of the threads will execute 4 instructions, and they will all have a SIMD, you'll have a SIMD utilization of 100% in that case also. Now the question is, how can you come up with that SIMD utilization of 67 divided by 256? And that's the part that I don't want to give out exactly. Does that make sense? So if you have, let's see, if all threads take the branch, your SIMD utilization is 100%. If no threads take the branch, again, your SIMD utilization is 100%, right? So how do you get close to 67 divided by 256? It's about a quarter, that's right. Yes. So if you look at 64 divided by 256, how do you get this SIMD utilization? Well, only 1/4 of the threads actually take the branch, right? Does that make sense? But that's not exactly true, because all of the threads actually execute the branch. So if you look at this branch, load, load, load. Actually, I might have solved the question for you, but that's OK. So all of the threads will execute this branch, regardless whether the branch is taken or not taken. Right? Now, to get to 67 or 256, you need to figure out what fraction of the threads actually take the branch. Right? And that's your answer, kind of. Right?
Couldn't you then
Yeah.
make it so that none of them take it?
None of them take it?
Then you would be executing. This is predicated, right?
That's right, exactly. That's predicated.
Which
So
means you still have to go through the loads, even if you're not.
exactly, yes. So think about SIMD utilization as you have 64. So for the branch, you have 64 branch units. And all threads execute the 64 branches, regardless of whether the branch is taken or not. So all 64 threads will be really utilizing the entire lanes. Whereas for the load, you still have 64 load units, but your data pattern is such that only 1/4 of the threads are actually executing and utilizing the load units. Does that make sense? So if you think about it, for one warp to be able to get 67 divided by 256 utilization, for this warp, all threads will execute. So you have 64 lanes utilized for the 64 warps. Here, you really would like to get 16, 16, 16, right? 1/4. So only 1/4 of the threads should really take the branch and execute the loads. And if you add these up, what you get is, I hope, is that right? Did I do this right? Maybe it should be 17, huh? Oh, 67. Sorry. I made a mistake. Yes. OK. Well, let's go back. So let's think about this, right? You're executing 4 instructions for each thread: branch, load, load, load. OK? So I got the number wrong because I was thinking something else. It's really to be able to. So for a given warp, what's happening is you're utilizing 64 of the branch units for the branch instruction. OK? Now, what we would like to get is a SIMD utilization of 67 divided by 256. For the load, we have 64 load slots for each of them. And we'd like to be able to get a 67 divided by 256 utilization for the entire warp, for the entire execution. Which means that you should really be executing one of the loads, right, in the thread. Make sense? So only one thread should be taking the branch in every warp. That gives you the 67 divided by 256 utilization. So if you think about it, you have 256 slots in the entire thread to occupy. And for the branches, all 64 threads are actually occupying the slots. For the loads, only one thread is executing within the loop. And all of the other threads are predicated off, basically. They're not executing. OK? Yes?
You said that if they all take the branch, it gets 100%
Yes.
utilization. I get that.
Huh?
You also said if they all don't take the branch, it's also 100%
Yes.
utilization. Why is that?
If they all don't take the branch, then what happens is they all execute only the branch, and no one executes the internal part of the code, right? They just go out of the loop. Right? That's the reason. Only the branch is executed.
But do they still get all the slots? But there's still be empty slots?
No, because they all don't take the branch, and they go off whatever is happening later on, right?
So they would never make the slots?
Exactly. They will never need the slots, right?
The slots are only making. The
Yeah.
slots are only made the first time.
Yeah. Yeah. Think about. Oh, say it again.
The slots are only made the first time you see it.
Exactly. Yes. So if you think about it, what's happening in execution is you have this warp that comes to the branch. You fetch the branch for all of the threads in the warp, and then you execute it, and then you figure out the direction, and then later on you fetch the next instruction. Right.
So they're like dynamically generated.
Well, they're not dynamic, but it's fine-grained multi-threaded, right? What happens in the GPU pipeline, as we've discussed, is you fetch one warp, and you fetch the next warp, and you fetch the next warp, next warp, and you don't fetch an instruction from the same warp until the instruction for that warp is complete, right? So if none of the threads actually take this branch, if none of the threads go into this loop, they will all execute one warp will execute the branch, and they will go to whatever code comes after that. Right? And we don't have anything over there, so you don't need to deal with that. Does that make sense?
Yeah.
OK.
So the worst case is actually this case where you only execute one piece.
That's actually true, yes. In this case, this is the worst case. This is the worst. Actually, did we ask it? I don't remember. But
Yeah, it's later.
OK, it's later. This is the worst possible case, because if none of the threads actually execute, then your SIMD utilization is 100%. If none of the threads go into the loop. And if all of them go into the loop, then all of them execute the loads, and it's 100%. The worst case is one thread executing this loop, and all of the 63 threads in the warp having predicated off, if you will. Right? That's a fun question. OK. So the question is not that, though. When we measure the SIMD utilization of this program with one input set, we find that it's 67,256 divided by 256. What can you say about arrays A, B, and C? That's the question, actually. Now you figured out how you can actually get 67 divided by 256, right? Only one thread should be executing. Only one thread within a warp should be executing these loads. Well, now we can say something about A, B, and C. Well, what determines the execution of this loop iteration for a thread? Whether bi is less than 4444, right? So within a consecutive, so how are these threads generated? Basically, you have an array B that has 1 million elements, right? 1 million. And you chop it into pieces of 64, because each loop iteration is a thread, as we told you, which is how GPUs are programmed today, actually. And each I is handled by a different thread in the same warp, right? Make sense? So this is basically what a warp deals with. 64 threads in a warp. Deal with consecutive 64 elements in the array. And what we figured out is only one of them should be taking that branch. That tells us that only one of the values in the chunk of 64 values, 64 consecutive values in this thread should be less than 4444. We don't know which value. We cannot say anything about that. But one of the values within the chunk of 64, consecutive 64 elements of the array should be less than 4444. That's what you need to write there. Make sense? That's what you can say about array B. And you can say nothing about array A and C, because this SIMD utilization doesn't tell you anything about arrays A and C, right? Does that make sense? OK. I think I've kind of solved this for you, but OK, not the whole thing. Well, I've given you this one also. Is it possible for this program to yield a SIMD utilization of 100%? Yes. Yeah, we've already discussed that, right? If yes, and the answer is yes. If yes, what should be true about arrays A, B, and C? Again, we cannot say anything about A and C, but we can say something about B. There could be two cases, right, when you get SIMD utilization of 100%. One case, all threads actually take the branch and execute the loads, which means that all of array B's elements are less than 4444. And the second case, none of the threads actually take the branch, which means that all of array B's elements are greater than 4444. That's it. That's the answer. Are people clear on this? OK. You can imagine variants of this question also. OK. Is it possible for this program to yield a SIMD utilization of 25%? No. Why not?
Because that was the worst case, and it was a little bit over 25%.
Exactly, yes. So what does it take to get 25%? Yes?
So it's not averaging across all the warps.
It's not averaging across all the warps.
So like maybe some stuff like you have a different mix of what's executed on one warp, what's not.
I'll have to think about that. But even then, in the worst, this is the worst case, right? Even if you do that average,
It would only be higher or the same.
exactly, it'll only be higher or the same. You can think about it and convince yourself that that's the case. OK? But this is really the worst case, right? Yeah, let me try to. The reason that's the case is because you can never below this, to get below this utilization for any warp, there's no way, right? There's no way you can get utilization below this value for any warp, right? Because only one thread in the warp takes the branch to get this utilization. If you go to 0 threads, you get 100% utilization, because none of the threads will execute this. Does that make sense? That's why this is the lower bound. OK? That's why this is a fun question, actually. OK. Any questions? Any more questions on this? But you can look at the past exams. We've asked similar questions. And I'm not going to spoil it for you. But let's see. Yeah, I don't know. Maybe it's not here. I thought it was here. All right, maybe it's in another exam last year. OK. Does that answer your question, Julia?
Yes.
OK, good. What else? Yes?
Can you explain more thoroughly what predicate combining is?
Oh, what predicate combining is. OK, that's a good question. Predicate combining, let's bring up the slides. But the basic concept is, instead of compiler generating multiple branches for different conditions, condition testing, it combines the predicates together and generates one branch. Let's go back to that slide to give you the code example too. And I'm hoping that, oh, this is S13. Lectures. I don't know if we covered it here, but let's try it here. There you go. Okay, this is different from predicate execution. But if you look at this piece of code, there are 3 conditions that are tested, right? If A equals B and C less than D and A greater than 5,000, then go into this loop. Now the compiler can actually generate 3 different conditional branches for this, right? Or maybe even more. Or what the compiler can do, basically if the compiler can test if A is not equal to B, then it can jump out of the loop, right? And then it can test if C is not less than D, then it can jump out of the loop. Then it can, another branch for jumping out of the loop. And the compiler can test if A is less than or equal to, is not greater than 5,000 and have another branch test that condition. So you can have 3 branches testing that condition and jumping out of the loop. And if none of the branches jump out of the loop, if all of them fall through, you can execute that. That's 3 branches. Or what the compiler can do is compiler can compare A and B stored into a general purpose register. And then compiler can compare C and D stored into a general purpose register. Compare A and 5,000, store the result into a general purpose register. And then logical AND, all those general purpose registers to generate a condition. And then generate a branch that tests just that condition. Now you've combined, if you will, all of those predicates into one condition that's tested by just a single branch. Make sense? That's the idea of predicate combining. That way you eliminate branches. It's a way of eliminating branches at compile time. Now I can go through the upside and downside. We've discussed this. Basically, that's the upside. You have fewer mispredictions. Instead of predicting multiple branches, you're predicting only one branch now. That's good. The downside is possibly unnecessary work, right? Because you need to combine all of the predicates to determine the branch condition, you have more operations, first of all. And you may delay the resolution of whether or not you go into the loop or not. For example, in this case, you have, I think one of you, when I gave this lecture, mentioned that this gets rid of short circuiting, right? What is the idea of short circuiting? In C, for example, you first test if A equals B. If that's not true, there's no reason to test the remaining conditions, right? Without predicate combining with 3 conditional branches, you can do that. If A is not equal to B, you don't need to execute the instructions that actually do those tests. But with predicate combining, even if A is not equal to B, you still have to do all of those tests and then do the branch afterwards. Make sense? So you get unnecessary work. Possibly unnecessary work. Okay. Yes?
So it would take like 2 instructions to AND it, right? Because you would AND 2 things and then AND 2.
That's right, yes.
Okay, so it adds more code too.
Mm-hmm. That's right. You had something?
So systolic arrays are also on the exam?
Systolic arrays are also conceptually on the exam, yes.
Okay.
We covered that relatively quickly.
Yeah, could you quickly go over that?
Yes, we can go over that. And there is actually a final question, I think, that you can take a look at from last year. Actually, I would recommend going through all of the questions in 447. Maybe we can put up the final exam too. What do you think? Because those would be a good... Oh, it's in the homework. That's good. Well, yeah. So let me I guess clarify it. I'm not going to ask you detailed questions on systolic arrays, but you should really know the concepts. Okay. Okay. Let me go over the concept though. But definitely do the homework question for the final exam or the next exam. So let's just talk about the concept. Basically, the concept is very simple. Instead of keeping loading data, processing on it, and storing data, and then having another processing element load data, process on it, and store data, you chain a bunch of processing elements such that they operate in a pipeline manner. Make sense? You send the data in this case, it's a linear array of processing elements. The first processing element operates on it with some, and operation could be fixed as we've seen in the convolution example. It takes in some input data and then outputs the result, which is chained to this processing element, which takes in that input data and perhaps some other input data, and then outputs the result. And then this processing element takes that, processes it, and sends it to the next one, dot, 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 right? And you can have fixed function processing elements. When this was originally proposed, this was to enable image processing, and you have fixed function processing elements that did convolution, for example, on input data coming from the image. This is a linear array, but you can think of it as a two-dimensional array also, right? You can actually input the x and y dimensions of an image and process on them in these different elements, if you think about this. And this was the exam question from last year. But I can tell you that I'm not going to ask you a question like that in this exam. So you can be so what you can do is you can have inputs coming from the left and right, and then connections between the systolic elements, the systolic arrays, like this. In this case, these are directional, unidirectional connections. But for example, this could be xi plus 1, xi plus 2, xi plus 3, and yi plus 1, yi plus 2, yi plus 3. And you could be computing something else, output I plus 1, dot, 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 right? Or output xi. I didn't do the x and y right, I guess. You could transpose it in your mind. Output y. OK? And the idea is when the systolic array receives both of its data elements, it basically processes it and sends a result to the next part. And then when this receives its data element coming from, and you will be pumping data elements every cycle. So this is the first cycle you pump data elements, right? And when the data elements collide at a processing element, you actually generate the result and send it to the next. So every cycle, some operation happens. And the next cycle, you can pump in, for example, xi plus 4 over here, right? And xi plus 5, xi plus 6, and xi plus 7. So for example, you could do averaging of an image. You could zoom into an image by having this regular structure. Does that make sense? If you want to see the exact example, the thing is you need to carefully orchestrate the data, pump in the data at the right time such that the data elements you want to be computed on at the same time in a processing element arrive at the same time. That's the difficulty in a systolic array. You need to ensure that the data elements, in this case, I didn't do a good job, I think. For example, if you want to ensure that yi and xi are operated here, this is fine. But if you want to ensure yi is also operated on xi plus 2 in the same cycle, this doesn't work, right? Because by the time xi plus 2 arrives here, yi is still here, right? You should be pumping in yi every cycle if you want something like that. Well, even that doesn't work, right? You should be pumping in no ops, for example, no data, such that they all arrive at the same time. OK? But this is for image processing tasks. Well, one example is image processing, such that you have the regular inputs, regular outputs, and you do similar things on the data. OK. And I think, let me show you the question in the homework. Well, I guess it is in the homework now. That's right. We put it in the homework. That's what we try to do to prepare you for the exams. But if you look at the homework 4 handout, there is a question. Yeah, programming a systolic array. That was a final question, I think, that gives you the structure of an element, and that tells you that we would like to do this matrix multiplication. And then the question is, if you have a systolic array that looks kind of like this, a 3 by 3 systolic array, how would you put the elements inside such that you get that result? OK? Yes?
Can we not have questions like this because we haven't done it in the homework yet?
Yeah. No, we won't have a question like this on the exam. That's right. Yeah, that's what I promised to you.
Okay.
OK? Yes?
We'll also have to know like the code optimization that the compiler does, like super blocks and that stuff, right?
Yeah, you should know the concepts. That's right. And there's an exam question, past exam, that you should definitely take a look at.
Yeah, but generically, the concept is that you want to get as much code together into one block, and you might have to fix some stuff up if you can't.
Exactly, that's right. That's right. The concept is, if you have a single basic block, there's very little opportunity for reordering the code, right? You watched the video from last year, right? Was that clear, by the way? You would prefer the video or me lecturing?
You.
Yeah, unfortunately. It's easier. I thought that was me, but yeah. Yeah, I was out of town, but I did want you to learn the static instruction scheduling. In fact, my flight got canceled this morning, so I was almost not making this review session. It's really amazing. There's nothing in the weather, and they canceled the flights based on prediction information. And the prediction is wrong. Anyway. So don't commit. I guess this is don't commit results with just prediction information, right? If they were computer architects who were taking 447, they wouldn't have canceled that flight. Or they would have waited a little bit longer to verify whether that prediction was correct, right? There's nothing on the ground in New York. OK. Anyway, enough of complaints. So what was your question? Oh, yeah, what was your question? Yeah, super block scheduling. So if you would like to optimize code, I don't want to go through the reasons for it. There are many reasons to optimize code. For example, for VLIW engines, right? In the lecture, I motivated it that way. What you would like to do is find independent instructions. But finding independent instructions within a single basic block is hard. And there are challenges if you have multiple basic blocks. How do you move an instruction? Because you do not know whether a branch will be taken or not taken. So if you move an instruction from the taken path or not taken path, you'll be wrong, right? So what the compiler, one technique to schedule code is to find more independent instructions is to find chunks of code that are much larger than a basic block. So how do you find that? Well, the compiler profiles the code, figures out what's the frequently executed path, and says it's very likely that the code will go this path. So I'm going to combine these basic blocks together, assume that the code will go this way. It's going to be a single entry, multiple exit block called a super block, and schedule instructions aggressively, assuming that the code path will take this way. Now I can find more independent instructions because I'm looking at, let's say, 6 or 7 or 20 basic blocks together instead of just one basic block. And I'm going to schedule code that way, right? And you've seen an example of it in the last lecture. Well, I can show you the slides, but I don't want to go over that in a lot of detail. Let's see. There should be a better way of doing this. I guess opening it up everywhere. No, that's not what I want. I guess it didn't matter. Oh yeah. Yeah, trace scheduling has a similar idea. And there's an example with trace scheduling, actually. Trace scheduling has similar issues with fixed-up code. Superblock just ensures that you don't have the side entrances into the trace, right? Let's go through trace scheduling very quickly, actually. But basically, this is the concept, right? Instead of trying to schedule instructions within a single basic block, these are basic blocks, you combine, you find the frequently executed path, and you form a trace out of it, right? And schedule instructions within that trace. This is what it shows. You reorder instructions as if this is the code that you're going to execute. Right? Now you can find a lot of opportunities to find independent instructions. Now the question is, obviously, this is not the code you're going to execute if the branches don't go this way. Then how do you handle that? And that's the idea of fix-up code. If some branches branch out of here, well, what you need to do is add some fix-up code such that you undo the things that you shouldn't have done if you went this way. Because let's say you moved an instruction from here all the way here. And this branch over here is going out. Well, what you need to do in that case is you need to undo that instruction before you go out. And that's what this fix-up code over here is. Right? We've seen this actually earlier in one case. I don't remember which lecture it was. We briefly talked about undoing an instruction, right? Actually, it was one of the instruction scheduling lectures. So basically, the trade-off is you combine multiple basic blocks and schedule instructions aggressively. But this is, again, speculative because this is based on this frequently executed path. And if the machine doesn't take that frequently executed path, you still need to maintain correctness. And to maintain correctness, you add this fix-up code. OK? Yes?
I guess I'm just confused about, this isn't super important, but how does it like define the most frequently executed path?
Oh, how does it find? That's based on profiling. That's a good question, actually.
Because it's like it hasn't compiled it yet, so I can't run it.
Oh, so it can run this program, right?
Yeah.
It compiles this program. So what happens is
and then it like recompiles it with
exactly.
Okay.
It's based on profiling this code. What it does is it profiles each branch, figures out what is the frequency of taking the branch or not taking the branch, taking the branch or not taking the branch. And then based on those profile information for each branch, you can figure out a path.
And then like how does it know what the inputs are going to be? Like it just uses all possible inputs?
Well, it uses the inputs that are available to the compiler. And that's the classic input representativeness problem that we've discussed, right? If your inputs are not representative, meaning if the path that you're going to follow dynamically is very different from what this is, then you're going to get bad code performance because you'll be taking these side exits, if you will, and you'll be executing this fix-up code much of the time. But that's true for any kind of compiler-based optimization.
Like if you're writing a program that a human uses, you don't know what they're going to do.
That's right, yes. If the input set significantly differs from the profiling input set that led to this code, then you're in trouble. OK? That's true for any kind of profile-based optimization, compiler-based profile. But this kind of technique, actually, this is trace scheduling. The difference between trace scheduling is trace scheduling has side entrances into the code that actually disable some optimizations, that prevent some optimizations that we've discussed in the last lecture. And to eliminate those side entrances, people have developed superblock scheduling. Yeah, I think if you go back to the last lecture, you'll see that that's the case. The infrequent paths interfere with the frequent path, right, due to side entrances. Whereas superblock is basically a trace with side entrances eliminated. What's a side entrance? Side entrance is this, right? You figured out this is your frequently executed path. These are the blocks you frequently execute. And because of the side entrance, you have a lot of optimization opportunity that's prevented. So to form a superblock, you actually replicate this block, and you now get rid of the side entrance into the trace. So a superblock is a single entry, multiple exit block. No side entrances. That enables more optimization and scheduling opportunity than traces because this incoming path doesn't exist. Right? Now you really have, if you enter the superblock, you know that you're going to only exit it. Nothing is going to enter it. And later we discussed the idea of hyperblock, right? Hyperblock eliminates control flow within the superblock also. Well, I guess it's another way of handling this, basically. You can actually include this in your block and use predicated execution. And that's the idea of a hyperblock. Hyperblock is a superblock with predicated execution. And all of these techniques are employed in today's compilers to extract parallelism. OK. Any questions? Now take a look at the superblock question, superblock optimization, code optimization, static scheduling question from past year. That can give you a good exercise. It's not hard. It's actually an easy question, like everything else, right? OK. What else? I don't think I'll take a break. So yeah.
So for superscalar execution, it doesn't necessarily replicate the entire pipeline, right? You could have some just shared resources.
Mm-hmm.
Like you could always just still have one multiplier, even
Yes.
though you have different pipelines.
Mm-hmm. Yes, absolutely. You don't replicate the entire pipeline. You can still have one multiplier and actually share it across the pipelines.
So the concept is that you're fetching multiple instructions at the same time, and you're dispatching them, but they might have to stop at several places.
Exactly. Yes. Exactly.
Okay.
Yeah, the concept is really multiple instruction: fetch, decode, execute. Resources are a totally different issue. Of course, to facilitate superscalar execution, you should really use multiple functional units. But exactly which ones should be replicated across the different ways of superscalar execution, that's a trade-off that the architect should make. So for example, usually adders are a good idea because addition is a very common operation. And if you have 4 wide superscalar engine, it's good to have 4 integer adders. But a multiplier or a floating point divide, for example, if you're not expecting to encounter floating point divide in all of your 4 lanes, almost all of the time, then it's probably not a good idea to replicate it. What else? Same with VLIW, by the way. VLIW is the same concept. You may have only one multiplier, and the compiler has to schedule the multiply operation in that lane, if you will, in that way.
The difference, though, is that for superscalar, the hardware has to figure out the interlocking.
Exactly.
It's a very long word. It's done by the compiler.
Exactly, yes. Yes?
So I understand branch delay, but you have one slide on branch delay with squashing. What do you mean by that? I couldn't quite understand from the
OK. Branch delay with squashing. Basically, that's the same as a branch delay slot, except you sometimes don't execute the instruction in the branch delay slot. So the idea is, well, I'll show up the slide, but the idea is normally branch delay slot means the instruction that comes right after the branch is always executed, right, regardless of where the branch goes. Now this is good, assuming you find an independent instruction. Branch delay slot with squashing, the instruction that comes right after the branch is executed only if the branch is taken. If the branch is not taken, then that instruction is automatically squashed. Make sense? You still, now you can put an instruction only from the taken path. And what does this enable? This enables you to put an instruction from the loop body. Let me go back to that slide. Oh, is it in this same? No, I don't think it's in the same lecture that I just opened up. Let's see. It should be here. Yeah, that's delayed branching. Yes. Basically, if you look at this, if you remember this, this was our normal code. And these are instructions. You have this branch conditional, and you have this loop, if you will. And A, B, C are all dependent on each other. And if you look at this, there is no way you can fill the delay slot if you have just delayed branch. Because what are you going to put here? You cannot put anything from the next iteration because you do not know if you're going to go to the next iteration. You cannot put A, B, or C from the same iteration because the branch is dependent on, there's a dependency chain. And you cannot put D or E into the delay slot because that will be executed only if the branch is not taken, right? So you'll put a no op. So somebody figured out that if you actually change the delay slot semantics a little bit such that the delay slot instruction is not executed if the branch falls through, if it's not taken, you can do something like this. You can basically put A from the next iteration of the loop into the delay slot. And if the branch is taken, you're going to execute the next iteration anyway. So it's good. You fill the delay slot. And if the branch is not taken, this is going to be squashed. That means you're falling through. So this is a very good idea if you actually have loops like this. OK?
How does that help? Like, because if you're like, let's say you just didn't have that and you didn't have a delay slot in general, wouldn't you be executing A if the branch is taken and not executing A if you just continue?
Yes, you would be, but now you can fill the pipeline. You don't need to predict, right? Because think about a pipeline.
But it's the same thing, because I assume you're filling it with something that's going to be predicated by the branch, right?
That's right.
So you can predict, and it's the same thing as having this fall through if your prediction is wrong.
That's right. So if you have a branch target buffer, yes, that's right. But this eliminates the need for a branch target buffer, right? So it simplifies the pipeline. Yeah, if you have all of the predictions, then yes, this doesn't help that much. Hopefully you'll do even better than this, right?
Yeah.
What else? There are some good questions. Should I take that as everybody's ready for the exam? Or should I take it as we need a break for 5 minutes? Or should I take it as we're done for today? What do you guys think? Who votes for the first one? I guess everybody's ready for the exam. That's the same as we're done for today. Who wants to take a break for 5 minutes and think about what questions to ask? OK, let's take a break for 5 minutes then. That seems like a good option. Just one thing based on a question I received just now. Here, of course, the hardware is more complex now, right? With delayed branch with squashing. The hardware now needs to have the ability to squash the instruction. It goes against, yes, exactly. It goes against the philosophy of delayed branching, right? The idea with delayed branching was the compiler ensures that the branch is handled in a way that the hardware is not complex. But now you need to be able to have the ability to squash or flush that instruction, depending on the branch direction. OK? OK, what else? There are lots of topics. Yes?
So I was trying to understand the benefits of checkpointing with like a future file, and like I don't see the benefits of checkpointing when it comes to having like out of order execution and the branch prediction.
Okay.
I don't see the benefit of what the checkpointing really does.
So the main benefit is if you don't have a checkpoint, what happens is you'll need to wait for the branch to be the oldest instruction, the reorder buffer, because that ensures that all of the incoming instructions get the correct registers. Does that make sense?
Yes.
Because if you do that now, wait, let me open up that slide. I don't think I have an example on that slide, but that's the main benefit. You don't need to, if you checkpoint, you don't need to wait for the branch to be the oldest instruction, such that when fetching new instructions. Okay, let's open that. Where is that? Yes, it should be here. There's a slide where I discussed. No, not this one. Oh, actually not at all that one. Yes. So this is what you need to do. If you have just a reorder buffer. Actually, let's go to the future file. How do you recover from a branch misprediction? You need to, basically what you need to do is you need to get the state at the branch, or right before the branch, right? That's what you would like to really get to. With a future file, what you have in the front is the future file and the state of registers at the front end, right? And then you have some instructions that are writing to some of these registers. And then at the end, you have a reorder buffer. And then an architectural register file, if you remember. And this is the architectural state. And this is used to recover the state of the future file once you have an exception or a branch misprediction. Now let's consider a case where you have a bunch of instructions in the machine. Oldest one is here. And then you have a branch over here and a bunch of instructions that come later. And you've just executed the branch. It could be out of order or in order, doesn't matter. And you've figured out that what comes after it was incorrectly fetched because you mispredicted the branch. Now what you need to do is flush all of the instructions that come after the branch. Right? You can do that easily by having a flush signal that goes over the machine. Right? Now that's not the problem. You can do that once you actually figure out the result branch. Right? Because all you need to do over there is to compare the instruction number of the branch to the instruction number of the remaining all instructions in the machine and flush the instruction if that comes after the branch. Right? The problem is the second part. You want the future file to get to a state at this point. Right? Actually, at this point. Such that the newly fetched, well, the second thing you need to do is you need to change the program counter to the correct program counter, right? Correct target. And that's also easy, because you know the program counter by the time you result. The third thing you need to do is the instructions that come in should really see the state over here. But the state in the future file really reflects the state over here somewhere, right? Because you fetched all of these instructions and they update the future file, right? Actually, you may have executed these instructions without overt execution, right? They've updated the future file. What you really need to do is to figure out the state that's in this architectural register file at this point in time and replace the future file with that.
So I guess what my issue was that so for out-of-order execution, the instructions in the reorder buffer could have written back the future file different times. But when it comes to, if you didn't have out-of-order execution, then like having checkpointing where you have like a future file associated with a particular branch and you update it is not really necessary, because the future file that you originally have is the future file. Once you actually get, once you like decode the branch and you execute it, you figure out whether or not the rest of the instructions you fetched were actually valid or not, then you can just use a future file of that state. But for out-of-order execution, you need to actually have future files associated with a particular branch.
Actually, it's true for in-order execution also, because if you have well, in-order execution with multiple cycle execute. Remember that all of this arose if we actually had multiple cycle execute. Some of these instructions may have updated the future file, just like out-of-order execution, because future file is updated when the instruction executes, right? Does that make sense? So the same problem exists in a machine with in-order execution with multiple cycle, different function units with different kind of execution latencies. Okay? And the problem is, just for everybody else's benefit, they may not have studied as closely as you, to be able to get the architectural state at the branch, well, you need to wait until the branch becomes the oldest instruction, right? And that's the problem with all of these different solutions. Okay? And checkpointing helps us, because now what happens in a checkpoint is you actually checkpoint the future file for this branch, right? Future file for branch X. Let's assume that this is branch X. And when you need to recover to this branch X, you just copy this future file for branch X into future file that you use for decoding instructions. Yes?
I understand that you need to wait for the branch to become the oldest so that you can write to the program counter and such, because that's when you take from the table and you write. But couldn't you just take it also from when you figure out what the branch is?
You mean the future file or architectural file?
Yeah, like so that you don't have to wait until it's the oldest in the reorder buffer.
Well, the problem is this architectural file is updated only when the instruction is the oldest. So if you actually take this architectural file at this point, when the branch is here, you will lose all of these different updates, right? Okay. So the problem is, basically the problem really is you don't have a register file state or map at this point, and checkpointing enables you that. The future file state is really here. The architectural file state is really here. And the branch state, well, what you really want is really here. And checkpointing enables you to get that. Make sense? Okay. And all out-of-order machines today checkpoint the future file or register alias table, if you will rename that to register alias table later on. For example, I believe alpha had 20 checkpoints. I'm not sure if that number is correct, but I think it is actually 20 checkpoints for the register alias table. Yes?
I'm just repeating a part of this question, but when you said in-order execution, no instruction after the branch would have completed till you actually get to know if the branch is correctly written or not, right? So then why do we still need a...
So that's not correct, actually. Yeah.
I forgot that the reorder buffer, the reorder buffer, the reorder buffer updates the future file, but the most oldest instruction in the reorder buffer at the top updates the architectural state. So the reorder buffer has a ton of instructions that have already actually updated the state. So when the decoder happens, we can actually see the current state of the architectural state without actually having to update the architectural state. Does that make sense? Like the reorder buffer has like a stack of
Yeah. Okay. So basically, there could be instructions here that could have updated, because they could all be independent but have different latencies. Think about it that way. They could all be independent, but you have an instruction over here that completes in one cycle, and that has updated. But there's an instruction over here that takes 4,000 cycles. Even though they're all independent, you cannot retire all of these instructions. Right? Think about it that way. Okay. Okay. What else? I guess back to the notes. You guys know about all of these concepts, right? I'm just flashing these so that somebody maybe remembers a question. Yes?
This sounds stupid, but if we have fine-grained multi-threading, do we still need branch prediction?
If we have fine-grained multi-threading, do we still need branch prediction? You tell me.
There are no dependent instructions
Mhm.
because fine-grained multi-threading, so we shouldn't have any dependencies, right?
Yes, we have.
Maybe it depends on how many threads you have.
Mhm.
Because if you only have 2 threads and your branch takes like 50 cycles to determine what it is.
But then that's not fine-grained multi-threading.
Oh, so it's
Yes.
fine-grained only when you have enough number.
That's right. So fine-grained multi-threading ensures that basically you have only one instruction from a thread in the pipeline, such that you don't need to handle dependencies. So the natural answer to your question is no, you don't need branch prediction of a fine-grained multi-threaded machine. What's what?
I haven't read Lab 4 yet. We're doing both of those things at the same time.
That's right. Yeah, it's just to give you an experience on both topics. That's a good question. That's actually a good question. Basically, you don't need branch prediction of fine-grained multi-threaded machine. You do need so what you mentioned is a simultaneous multi-thread, potentially simultaneous multi-threaded machine, where you can execute multiple threads, but it's not really fine-grained multi-threaded.
Okay.
Yes.
So with fine-grained multi-threading, is it usually assumed that the threads run in different address spaces, so you don't have memory conflicts?
Mm-hmm. That's a good question. Actually, that's correct. In fine-grained multi-thread machine, that's the assumption. But to support shared memory programming, there is load store handling that happens in machines. Well, we won't go into that. In the strictest form, yes. The answer is yes to your question. In the real-life complex form, the answer is no. Because pretty much you do shared memory programming, and it's very hard to guarantee that they actually run on a different address spaces. These are good questions.
So we should do branch prediction first for the lab, and then fine-grained multi-threading.
So that's a good question. I don't think we're going to test both concepts. So that's why I said do lab for A and B. You could do either one, I think. But my suggestion is do branch prediction first. That's for A.
Okay.
Yeah. You could do them independently, actually.
But they branch off from the same lab 3. They don't. It's not like you do one and then on top of that you're going to do fine-grained
Oh,
multi-threading.
okay. How did we specify that, Rachada? Rachada's thinking, so. All right, maybe we'll give you an answer.
Okay. And
At
the
the
other
end.
question is,
Yes.
do we have to do this off of the forwarding or the Stalin version of lab 3?
Off of the forwarding version, right? Yeah, it's the latest version of Lab 3. That's why if you haven't done forwarding, you should really talk with the TAs. Yeah. That's right, it's not that easy. What else? We still have 10 minutes if you want to ask more questions. Or we can part early. Yes?
Could you explain what the choice predictor was when it came to the, like when you have a hybrid predictor, hybrid branch predictor, what's the choice predictor?
Yeah. So the idea is you have a hybrid branch predictor, and you would like to figure out which predictor's prediction you're going to use. And that's the purpose of the choice predictor.
Oh, how does a choice predictor make that prediction?
Oh, that's magic. Basically,
I didn't explain the notes. I was confused.
Yeah, so there, let me give you, you're going to implement this as part of your lab, but let me actually open this up. It's definitely not magic. But you could think of different kind of choice predictors. We didn't go through all of them in detail, but I'll give you one example, which is used in Alpha 21-264, a real life example. Oh, there you go. Where is it? I'm pretty sure I had it somewhere here, but that's okay. Oh, there you go. Okay, so if you look at this, you have two predictors, a local predictor and a global predictor and the choice predictor over here. How do you make that decision? Basically, the choice predictor is indexed using the global history register, 12 bits. And the idea is it keeps track of which predictor was correct, right, for this particular global history. And if this global predictor was correct, then the 2 bits indicate that pick the global predictor.
It uses a saturating
counter? It uses a saturating counter. Yes, exactly. For the predictor that was correct. Yes.
Though they could have combined the two, right? It was just a choice to keep it simple, to keep the both predictors separate. So you know the one where you can XOR the program counter and your global history to
Yes.
have.
Oh, you could have basically said have a PC XOR global history and index the choice predictor? You could do that, yes. That's
and
another way.
index some sort of global predictor. So that, didn't we have that in like 2 levels?
Yes, so that's the G-share predictor.
Yes.
Yeah, that's basically global history XORed with program counter, and then you index the global predictor. You get a prediction out of that. Yes.
Which is more complicated. So here they chose to like not make the hardware so complicated.
That's right. Yes.
Okay.
Exactly. They chose not to include that PC information.
But
They-
there. Yeah.
Exactly. They include the PC information for purely the local predictor. Yes. But you could have had this local predictor and that G-share predictor over here.
Yeah.
Right. And then still have a choice predictor. Okay. So you'll implement something like this as part of your lab 4A. Yes.
We always miss in our BTB, or if we miss, do we just go to PC plus 4 automatically?
Oh, so that's a choice basically. That's a choice that the designer makes, but that makes sense, right? And usually in the machines, if you miss in the BTB, you automatically go through PC plus 4. Because if you miss in the BTB, you don't know whether the instruction's a branch. That's a good choice. Otherwise, what's the option? You could stall, but that's a bad choice, right? Yes, so the answer is yes. Actually, it should be somewhere here. Yeah, there you go. Yeah, if you don't hit in the BTB, you get PC plus instruction size. Okay? And you'll do this in your lab too. Yes?
Could you also just go off the global history?
You could potentially do it. The problem is you don't know whether the instruction is a branch, right? Global history indicates something and will give you some prediction. But you don't have the target. And you don't even know whether the instruction is a branch.
Know whether it's a branch.
Exactly, yes.
I thought this was for determining whether it was a branch that we have already taken.
Oh, no, that's...
Okay.
Yeah, if it was a branch that you have already taken, then you should have it in the BTB, unless it's a conflict miss, unless it's evicted out. Yes. So PC plus instruction size is a good choice. What else? Branch handling is definitely a good topic to study for the exam. Well, you knew that also. Yes?
Did we cover any preemptive, like memory dependence handling procedures? Like, I know that we talk about having like a store buffer where you keep like a buffer of all the current store addresses, and then like if the load that you're looking at does not have an address in a store buffer, then keep it going.
That's right.
Do we talk about anything else? That's for like detecting a dependence.
That's right. We did talk about predicting, but we didn't talk about how to do it. Yeah, we didn't talk about how to do it, but we talked about 3 ways of handling dependencies. If you have a load instruction and if you have a store buffer with one unknown address store, then the question is, what do you do with that load, right? We talked about 3 different ways of handling it: conservative, aggressive, and intelligent, right? Conservative one was to say if there's any unknown address store, just wait, keep the load waiting. The aggressive one was if there's any unknown address store, assume that the load is independent. That's one method of predicting, right? Just assume the load is independent and schedule it. And the aggressive one is try to predict whether the load is dependent on the store or not. Right? We didn't talk about exact methods of doing that. We talked about one method in alpha 21.264. It's in your reading also, right? And what alpha did was if you have a load instruction and then there's a store instruction with an unknown address, alpha initially took an approach of aggressive handling. Basically, it's aggressively schedule the load, and then later figured out whether that was the right decision or not. How do you figure out whether that's the right decision or not? Basically, when the store address is determined, you check whether the load actually overlaps with that address. If it does, then that was a wrong decision, right? Because the load went first. It shouldn't have gone first. And then what the machine did was to mark that load in the instruction cache with a single bit saying that do not schedule this load aggressively. Right? And the next time you fetch the load, you have that bit. And if you see an unknown address store in the store buffer and you're scheduling that load, you check that bit, and the bit says, oh, in the past when I scheduled this load aggressively, that was a bad idea. So I'm going to wait until all of the stores in the machine have known addresses, and I can check the address of this load against all of those stores. Make sense? So that's a more or less intelligent prediction mechanism. That's the only mechanism we covered. But there are a lot more complicated mechanisms that try to link loads to particular stores to make that decision much more fine-grained. And you don't need to know about that, unless you would like to. But that wouldn't be a good way of spending the next couple of days studying for the exam. What else? Yes?
So what kind of things do you recommend putting on the paper if it's very much like not memorization?
No. Well, ideally, if you study well for the exam, you don't need a paper.
Okay, fair enough.
But it's still good to put things on the paper because that's, while you're studying, it helps you, I think. But in the past, whenever I'd taken exams that had a single sheet of paper, I usually didn't need the paper. But definitely don't put the LC3B data path, for example. That would be a waste of your paper. We'll give you whatever is needed if you really need to know the definition of an instruction, for example. We'll give you the data path picture. Know the data path, of course, but you don't need to memorize it or put it on your thing. And you can see a past question, for example. Well, and the past question asks, what is this? We've added some structures. What are these structures useful for? So that requires you to know the data path operation. What else? Was that all? I guess so. Okay, yeah.
Where are we going next?
In the course, you mean? Well, next it's the exam. After that. Yeah, after that. Well, we're going to go into memory actually. A lot more into memory. I think we've covered all of the execution model. Maybe I'll talk a little bit more about systolic arrays. I'm not sure yet. But we're going to start with the memory hierarchy. We're going to talk a lot about caches, its interaction with virtual memory, advanced methods for caching, memory scheduling. So it'll be very memory focused. We'll talk about interconnects a little bit. We'll talk about heterogeneous multi-core processors. We'll talk about multiprocessors, cache coherence, synchronization, sequential consistency. A lot of exciting topics. But hopefully it should be fun because that's a huge bottleneck in today's systems. How to handle it. We'll talk about emerging memory technologies also, some non-volatile memory technologies that could potentially replace DRAM that we have today. Should be fun. You're looking forward to it, I can tell. Cool. All right, I guess this is a good time to end the review session then. Study hard and good luck on the exam.